Okay, welcome everyone to the International Public Safety Data Institute's July webinar. My name is Alex Trotman and I'm the Customer Success Manager at IPSCI, and we're thrilled to have you with us today. For those who may not be familiar with IPSCI, we're a collaboration of fire service organizations built from partnerships that we've had for many years. The IPSCI is a nonprofit research and data science organization, and we host these monthly webinars to provide information to enhance what you do at the local level and give you another opportunity to get insights for decision making at the operational, prevention, and pre-planning levels, all of which depend on good data resources. Today, we'll be going over the methodology for initial move-up plan and model that leverages historical incident data and GIS technology and provides recommendations that optimize a fire department's resource coverage. We will also explore how the operational data collected in NFORS can help inform decisions involving the placement of new units in a fire department. So before I turn it over to Tyler, I wanted to let you all know that we are recording the session so we can post it to our training tab on the IPSDI webinar. So you can go back and reference information shared or share it with others. And during this webinar, you will be able to use the chat function at the bottom of your screen to ask questions. So thank you all again for being here. And with that, I'll turn it over to Tyler Buffington.
All right, thank you, Alex, for the introduction. A little bit of an overview of what I'm going to talk about. I'm sure some of you are familiar with NFORS, which is the National Fire Operations Reporting System. But for those of you who are not, it is one of the central products of IPSDI, and it basically collects and analyzes large amounts of operational data from fire departments. As a data scientist, I'm a big believer that data is only valuable if it can inform action. So my work with NFORS data has largely been to think about potential decisions that NFORS data can inform and think about how it can inform those decisions. So in this presentation, I'm going to talk about two potential decisions that NFORS data can help with. These models are meant to inform human decision making. So obviously there's going to be some other factors that go into making these decisions, but these are going to be relatively simple and interpretable ways to use the NFORS data to help with some of these decisions. So one is going to be the purchasing of a new unit. So the idea is that if a department wanted to purchase a new unit of a certain type, they might want to know what the impact of adding that unit would be. And so I'm going to explore one way the data can help answer that question. And then another one is the move up question, which basically is for real-time coverage holes. Maybe a busy station has its resources deployed where they're already responding to other incidents. And then, if a new incident occurs, then there might be a coverage hole because that station is out of resources for that incident. So the question is, should maybe other units from less busy stations move in to fill in the coverage gap? So those are going to be the two decisions that I'm going to be looking at today. So without further ado, I'm going to go into the unit purchasing model. So a little bit of background. A lot of this analysis depends heavily on the concept of first due areas. So I'm going to talk a little bit about them. So the idea is that a fire department will typically divide up their jurisdictional boundary into a set of regions known as first due areas. And these areas identify the station that normally responds to an incident at a given location. So I have an example over here. So we have the stations, which are indicated by these icons, and then we have the corresponding first due areas, which are color coded. So for example, if an incident were to happen here, that's within the purple area, which is the first due area of Station D, which means that Station D would usually respond to that incident. It's usually in the best position to respond to an incident at that location. So what we see in the data is that the first due station does not always respond to an incident in its first due area. There are a variety of reasons why that might occur, but one that we're going to focus on is this. So we're gonna illustrate that with this simple animation. So the idea is we have two different stations. We have Station A and Station B, and then we have these first due areas, which we just indicate as these boxes. And so we're also going to say here that Station A and Station B have one unit. So maybe it'd be a ALS unit, and then the incidents we're gonna look at are incidents that require an ALS unit. So let's say that they both have their unit hou- housed at the station, and then let's say that there's an incident in the first two area of station A. Okay, well at this point, well, station A is able to send its unit to respond to this incident. Okay, and then let's say that there is another incident in station A's first due area. Well, station A cannot respond to this incident anymore because it sent its only unit. And so another station, in this case, in the simple example, there's only one other station, station B, must send its unit to respond. And so generally, whenever there are responses from a non-first due station, that's linked to a longer response time. So to show that, I did a case study on one department, and we looked only at dispatches from ALS units. And so I don't disclose the identity of the department just for confidentiality reasons. But what we see here is for each first due area, so there's 6 first due areas in this station, so there's 6 plots. So this is the first due area of station A, for example. What we do is we break down all of the dispatches of ALS units into 2 groups. So we say, okay, did the dispatch come from station A or did it come from some other station? Um, and so then we get 2 different response time distributions. And so these are known as CDF plots, which are cumulative distribution plots. And they are a way of visualizing a statistical distribution. So let's say that, as an example, let's say that in the first due area of station A, you have an incident and it comes from the first due station, which would be station A. Well, then you can look at the 80th percentile of that response time, and then you can say, okay, in that scenario, there's about an 80% chance that the response time would be below about 400 seconds. And so the difference between the blue and red curve are a way of visualizing the consequences of non-first due dispatches. And so what's kind of interesting to see here is that the consequences of non-first due dispatches vary by first due area. So we could see that in the first due area of station B, the difference between the blue and the red curve is relatively small compared to station F, for example. And this is likely because in the first due area of station B, there are multiple stations. And so station B does not respond and some other station responds. It probably is not coming from that much longer of a distance. Whereas in station F, or the first due area of station F, if if station F does not respond and some other station has to respond to an incident in that region, then that's linked to a far longer response time. Um, so we kind of established that for each first due area, there's 2 different lotteries of response time. You can think about 2 different statistical distributions. And so the next step in the modeling framework is we actually extend that idea of thinking of response times as a lottery to um, basically the entire incident, right? And so there's other uncertainties. So we basically say, okay, well, if you have an incident, all right, and so these are again, we're and if, for the data shown here, we're limited to incidents that require an ALS unit. But we say, okay, if you have an incident, there is an uncertainty of where that incident will occur, which first due area. And so from the data, we can learn these probabilities. And this is just saying, okay, 27% of the incidents happen in the first due area of station A, 13% happen in the first due area of station B, and so forth, right? So we can think about, okay, the first draw, right? If we say there's an incident, the first kind of random draw is where it occurs, right? And then within where it occurs, then we say, okay, there's a certain probability that um, the dispatch will come, or the response will come from a first due station or not from a first due station, right? And then we said that for each station, given that it comes from for each first due area, given that comes from the first due station, there is a lottery of response times. And then if it doesn't come from the first due station, there's also a lottery of response times. So this is kind of one way of thinking about the uncertainties that affect response time for a given incident. Um, and so what we've done is we've built a model that simulates the effect of adding a new unit to a station by modifying these probabilities here. So I'm not going to go into details into how that calculation works. It's a little bit beyond. It's a little bit complicated beyond the scope of this presentation. But the idea is that if you add an additional unit to a station, then that station now has more resources, and so it's less likely to be in a position where it cannot respond to incidents in its first due area. Um, so by simulating changes to these probabilities here, we can actually simulate the improvement in response time, total response time over the span of a year by just modifying these probabilities based on what we learned from the data. So the end result of this model might be something like this, where we say, okay, if we added an extra unit to station A, then in that region, more of the responses would come from the first due station. And so then we have an estimated yearly improvement. So this is like the total number of minutes in response time that would be reduced based on the fact that more responses would come from the first due station. And you can simulate this for each of the stations. And so then from here, you can see, okay, this indicates that um, there is an optimal improvement from adding a unit to station A, which kind of makes sense in a way because station A has the busiest first due area. But it is interesting to me that um, comparing station A versus station F, because we see that station F has the most significant consequences of a non-first due dispatch. However, it is the least busy station. So it's kind of interesting how those trade-offs basically balance out and how the model looks at that. And it says, okay, there is the maximum improvement from adding it to the busiest station, at least here. So this is one way that the data can help inform decision. Again, it's not, I would not say, hey, use this as like the sole recommendation, but this is one sort of quantitative way that people can use the data to gain a clearer picture of sort of the coverage of their department to make a decision like this. So next I'm going to talk about the move up model, which is more for addressing real-time coverage holes. So first I'm going to talk about a visualization that I use to help understand the move up model. So what it is it's just an incident density heat map. And so this is a very common visualization where hotspots indicate where incidents are most likely to occur. We have very similar visualizations in fire care, so those of you who are familiar with that. Um, and so this, for example, would be probably downtown where a lot of incidents happen. And then out here, this is probably a more rural area where incidents do not happen as much. And then you have sort of not quite hot spots, but hotter spots out over here. So this helps understand demand where resources are needed the most. So what I thought was interesting is that for each of the stations, which are these black dots, using GIS technology, you can actually derive a travel time polygon around each station. And so you can set it to whatever you want. So I used 8 minutes. Sometimes you can use 4 minutes, 6 minutes, whatever. But just for this, in the actual products, we're going to make this a knob where users would be able to specify whatever their definition of coverage is. So you could say, oh, we wanted to find coverages within 8 minutes of a station, for example. But the idea is that for each station, you can get a polygon that indicates the region that is within an 8-minute travel time from the station. And then we can basically plot the union of all those polygons. And so this checkered pattern here indicates everywhere in the department that the GIS software said was within 8 minutes from a station. And so then you can plot the heat map. And the idea here is that it shows the uncovered regions. So if there's a hotspot that's covered, then you will not see it in this visualization. And so it says, okay, of what you want is the regions that are outside of that travel time, you want them to be very low incident frequency. So this is kind of one way of visualizing coverage holes. So if you see something red that's outside of a 8-minute or however minute travel time polygon from a station, then that indicates a coverage gap where incidents are happening regularly, and they're also outside of the drive time polygon. But a key assumption here is that each of the stations actually are able to respond. So when you make that map, you say, okay, well, it's 8 minutes away from a station, right? But that only is meaningful if that station has a unit available to respond. And that might not always be the case because some incidents will pull resources away from the station. So here's an example I found in the data. This was a large factory fire that happened at this location, and it pulled resources from a bunch of different stations from the surrounding areas. And what I did is I said, okay, if a station responded, so this is based on the assumption that it only has one engine. So this was based on an engine analysis, whereas before it's based on an ALS unit analysis. But if we say, okay, if it only has one engine, then the resources for engines are depleted from that station. And so then what we do is we basically turn off their drive time polygon. And so regions that are close to that station might not be covered anymore. And so now we get this new resulting coverage map. And you can actually see that if these stations are not able to respond anymore because they sent their units to this incident, then we actually have this hotspot, which is now uncovered. And so now the question is, are there other stations that have units maybe in not as hottest spots where there's not as high of an incident frequency? Should they send their units maybe to these stations to fill in the gaps? And so that's kind of the point of the move up model. And it's in its current state, it's really, really simple. We wanted it to be really interpretable and transparent, not to be used as a real-time tool yet, but to be more of an interactive tool that users could use to simulate hypothetical scenarios, and then from there provide feedback so we can understand better the needs of the individual departments, and then from there we can iterate it to be more robust and sophisticated. But right now it's really simple. And so the move up model consists of solving two optimization problems. So the first optimization problem, it says, okay, if we have only n units available, right, then we need to figure out the n best locations for them to be. And so when we say locations, we say that we assume that the units can only go to stations, right? There might be some cases where, like, to get optimal coverage, you could park a unit at a 7-Eleven or something like that. But in the current iteration of the move up model, we say, okay, the only candidate locations are station locations. And so this is also intended to be used where there is a shortage of units, meaning that there are fewer units than stations. So if we have only n units available, then we have to determine the best n stations for them to be. And then once we've determined that, then we have to have a movement strategy. And we say, okay, what's the best strategy for moving units from where they are to where we've determined that they should be to maximize coverage? So I created this really simple example of the move up model to give kind of an intuition for how it works, because it can be a little bit overwhelming when you just look at like how it runs on actual data. Um, so we consider this simple example here where we have it should be, that should say 5 stations, but we have 5 stations, and then we have 12 historical incidents, right, which are indicated by these X's to indicate the historical incident locations. And we also say that we only have 2 available units, and they're currently at station A and station B. So the question is, should we move the units that are at station A and B to maybe some other stations to maximize coverage given this situation right here? So the first thing we do in the move up model is we determine the station whose drive time polygon would cover or include the most historical incidents. So in this case, that would be station C, because these circles indicate the drive time polygon, and we see that there are 6 incidents that fall within station C's drive time polygon, and so that would be the one that we would include. So you could see the number of covered incidents for each of the stations at this point is listed out, and so C is the best one with 6 units. So first thing we do is we choose station C, and we have 2 units, so we can choose 2 stations. And so we've chosen one, and now we need to choose another one. And so now we basically repeat the same step, except we say, okay, the incidents within the drive time polygon of station C are covered, so we're going to exclude them from the analysis this time around. And so I've indicated that by covering up station C's drive time polygon. And now from here, we choose the one that the station that now includes the most uncovered incidents. And so we made another table here, and we see that the best improvement now would be station D, which includes 3 uncovered incidents. And so then that's it in terms of choosing the optimal station. So we only have 2 units, and we chose the 2 best stations that give us the best coverage based on historical incident locations. So now that we have our 2 ideal stations, we need to figure out the best strategy for moving the units from where they currently are to these ideal locations. So what we do there is we compare different strategies for movement. So keep in mind, again, we have 1 unit at station A and we have 1 unit at station B, and we want a unit at station C, and we also want a unit at station D. So that actually gives 2 possible strategies. So we have the blue strategy, which would be moving station A to station C, and then it would also involve moving, or it would also involve moving the unit at station B to station D. So that's the blue strategy, and the total distance traveled from that strategy would be 1 plus 2, which is 3. Um, and then we have the red strategy, which would be moving the unit at station B to station C, and then moving the unit at station A to station D. And then the total distance traveled from that strategy is actually 2.4 miles, which is shorter than the distance traveled for the blue strategy. So our model right now would recommend the red strategy instead because it involves the least amount of movement. So it's relatively simple. There's definitely going to be a lot of edge cases where the movements are not practical, or the improvement in coverage is not worth all the movement that the model might recommend. But in its just current simple form, we believe it's relatively simple and hopefully pretty interpretable. Um, so based on that simple example, that should give kind of an intuition for how it works for a more complicated case. So we just use little circles to indicate the drive time polygons in the previous example, but in the actual model, it uses the complicated drive time polygons that we get from a GIS service. And so you can see they're a lot more, the shapes are kind of a lot more complicated, as you see here. They're not just little circles. And then also too, we only looked at 12 historical incident locations, whereas the actual move-up model would look at thousands. It would look at pretty much the entire um, incident history that is recorded in Inforce to determine the best places for the units to be. But at the end of the day, the full model is just an extension of that simple framework I described. So we do have a move up model user interface under construction in Inforce so that people will be able to sort of play around with it. And so this is sort of in the early stages, but I just took a screenshot of what we have. And so the idea is like, so at this point there's circles, and down the road we're going to integrate the actual drive time polygons. The idea is that you could put in a current situation for your department, say, hey, here's where our units are currently. And then you could look at this optimized strategy, and then it would tell you how much it improves the coverage, and then it also tell you the recommended moves. And so then from there, um, the customers could experiment with different strategies, and then they could also provide feedback into whether they think the recommendations make sense or not, and if they don't, why not. And then from there we can iterate the model and the user interface to a better and better product. So that's pretty much the overview of the move up model. So conclusions for the whole presentation: we discussed 2 relatively simple models that can help with resource allocation decisions, a unit purchasing model and a move up model. Again, they're relatively simple. They're not meant to replace human judgment. They're, in a lot of ways, they're kind of naive, and they are no substitute for somebody who has a lot of experience, especially within a certain department, but they're just meant to provide quantitative information to support human decision making. And there is research underway to continue improving these models. And a lot of that research is going to depend on feedback from Infor's users to tell us whether the models are giving recommendations that make sense, or if the models have certain blind spots, and we will basically iterate them to a better and better product. So that's it for my webinar talk. I am now open to any questions the audience may have.
Okay, thanks, Dr. Buffington. Sorry, I had to get my camera turned on there for a minute. There are no questions right now, and if anybody does have questions, throw them into the Q&A, but I'd like to kind of throw something out there. I'm assuming that the people on here, they're here because they understand NFORS, but maybe there's somebody who isn't. So can you give us a real short explanation of what NFORS is?
Yeah, so Infor is the National Fire Operations Reporting System. So it's a data system that basically takes operational data from fire departments, and then it ultimately normalizes it into a uniform form across the different departments, because we find that departments in their current data reporting software, oftentimes they have a bunch of different formats, XML or whatever. And so NFORS will basically normalize it and then also provide a bunch of additional information. So we find that some departments might record their incident locations, but NFORS will take the incident locations and the time, and then also add a bunch of weather information as well, for example. So it normalizes their data, enriches them, and it also provides dashboards that allow for informative visualizations to help decision making.
And every department already has an NFORS dashboard, doesn't it?
Yes, I believe so.
Yep. So it's something that's out there for everybody to use right now if they want to. You had mentioned that the move up model is under development. Do you have any ETA on when it might be ready for prime time?
I do not at this point. So I actually am going to meet with some of the people who are working on the development of that next week. So I'll probably have an update next week on that, but I do not have an ETA at this time.
Okay. Well, I don't see any questions in the Q&A, so really appreciate it. And with that, Alex, I think I'm going to toss it back over to you.
All right, sounds good. Thank you all so much for joining us today. As we mentioned previously, we'll be posting the recording to the IPSCI website in the training section, so please feel free to share it with others. Ed has linked our website in the chat. And if there aren't any other questions, then have a great day, everyone. We hope to see you all next month for our August webinar.
Thanks, everyone.